Section 6.6 Derivatives of implicit functions. Suppose we have arrangement of x, y, and z and so on. It goes to 0. In fact, c, we consider z as a function of f of x, y, but we haven't plugged it out of here yet. We'll just let it sit in there like as an implicit function. And this particular equation, right, this whole arrangement here, we call it a function of x, y, and z, and we set it as 0. So this particular relationship is one is related to the other. So anyway, so when this happens, suppose we're told to find partial z, partial x, and partial c, partial y. How would we do that? Well, you just go about, well, cranking it up. The old-fashioned way, which we'll do right now, and after we do this problem, we'll figure out a theorem to do this systematically. But for now, we'll do it the way we have done it in the past, which is you take everything with respect to x, the partial derivatives. So the first one becomes 2x. So take derivative of everything with respect to x. You get 2x, and then plus, okay, this is x, and there's z. C is a function of x. So then we use the product rule. So 2x and then partial c, partial x, plus c times the derivative of that, which is just 2z, and then plus that becomes 2z, then partial c, partial x, and then this one becomes minus. Now y is a constant in what we're doing here, so it'd be minus y, partial z, partial x, and the rest are constants, so, and then it all equals to 0. Now if this is the case, then we are trying to find partial z, partial x. So we have partial z, partial x equal to, there's one here, and one here, and we just isolate it. And so we have to move everything over to the other side. We have minus 2x, and then minus 2z. That's about it, I think. There's that and that. And then divided by this thing right here is 2x. And then here's another one, 2z. And one more, which is minus y. So that's how we crank out the first one. And we claim that that's not all we're going to do. We're going to claim in a moment that there's actually a formula for this. And the formula states that the partial c, partial x is actually equal to partial f, partial x, divided by partial f, partial c. And that gets you partial c, partial x. Now if you check this real quick, what is partial f, partial x? Then you take everything with respect to x, and this time x, y, c are all independent, so then anything that's not x is a constant. So it becomes 2x plus 2z, and that's about it, okay? And oh, sorry, there's a negative sign here that I should mention. All right, so there's a negative sign, and then that's that. And on the bottom, what is partial f, partial z? Again, everything else is a constant. So with respect to z, you have 2x, and then 2z, and then minus y. So this formula does work out. But we haven't proven the formula yet. We'll prove in a moment that this formula works out in general. Now, in the meantime, we continue with this example. We try to figure out, let's see, that's one of them. Okay, the next one is with respect to y. If we take partial derivative with respect to y, then x is a constant, and then this becomes it becomes 2x partial z partial x. Okay, this is a 2 there, and then plus 2z, 2z, and then partial c, partial y. I mean to say y here. We're doing y. Okay. So 2z partial z partial y, which is right here. And then with respect to y, we have minus y partial z partial y, and then minus z, and then minus c, okay, and then equal to 0. And so out of this, we are trying to figure out what partial z partial y is. So we'll write it down here. Partial z partial y equal to, there's one here, and one here, and one here. And that's the only thing that isn't there. So we'll write down c on top. And what is the bottom? The bottom consists of 2x, and then plus 2z minus y, which is exactly this thing. And we claim that this is supposed to be minus partial f partial y over partial f, let's see, partial z. Now what is partial f partial y? If you take derivative with respect to y here, with everything being independent, then you have minus z as the only one that's on top, okay? And since we have a minus sign here, that becomes a plus. And of course, we already know the partial f partial c happens to be this thing. So this is the formula that we are claiming for, that is going to work for, well, anything, not just this one example. So we're going to actually prove that that is true. In order to prove it, we have certain conditions. That is, we have f, which is f is some kind of arrangement such that f of x, y, z is 0, and z is defined by f, x, y. Furthermore, f is presumed to be differentiable, and then z is supposed to have first partial derivatives. We'll not go in too deep about all those requirements. Just vaguely, we know that they both supposed to be, well, reasonable behaving functions, differentiable and everything. Now, if that is true, then let's define g. Then we will call g of x, y equal to f of x, y, and z, which stands for fx, small f, x, y. And then we will calculate the partial derivatives and see if we can get something to come out. In other words, see if we can prove that these two situations here are true in general. So to do that, we will take partial derivatives and let's see if it gets us anywhere. So partial g, partial x, and remember g as it is, as we understand it, g is equal to 0. And always. The 3 lines means it's always 0. It's not just 0 some of the time. Anyway, so partial g, partial x is equal to first partial f, partial x. With respect to x, then we have partial f, partial x, okay? And then plus partial f, partial y times partial y, partial x, but that's 0 because y is independent of x, so we don't have to write that down. And then the last time, this one becomes partial f, partial z times partial c, partial x. Okay. So we'll write it this way, and then, in other words, I'll write it another way is to save energy, we'll call this f1, okay? F with respect to x is called f1, and f with respect to z is called f3. Now, as I've mentioned, the g is, as we have defined, is always going to be 0. It's an identical 0 function, which means the partial derivative of g is also identically 0. And which gives us that partial z, partial x, is equal to negative f1 over f3 when you solve this equation. That is exactly what we've been claiming over here, okay, that this case works in general, not just in this particular example. And similarly, we have, since x goes with f1, we similarly will derive or can derive that partial c partial y is equal to negative f2, as in here. Okay, with respect y is f2 because everything is symmetrical here. So over f3. And that is the formula we are trying to drive at.